All right. You should be about ready to get started. Okay. So good morning or good early afternoon, everyone. And sorry, let me remove my echo. So my name is Alex Shim, and I am here to bring you the third week of Data Cabinet's reinforcement learning series. And for these 3 weeks, we've been trying to learn to create three very common models of reinforcement learning algorithms. The first week, we covered more machine learning algorithms. The second week, we covered policy gradients. And for this third week, what we're going to do is we're going to combine these concepts together to create um, to what's known as the actor-critic algorithms. And once again, if anyone has any technical difficulties, please let us know in chat, and we'll be ready to try to help out there. And um, I just wanted to mention that this is okay. I will change the font size or fix it with the window. Okay, and so what I'm presenting are project or Jupyter Notebook projects run on the OpenAI environment, which are for reinforcement learning algorithms. And the idea is that there's sort of a step-by-step idea of how you would construct these models. Not necessarily a finished product, but more like, well, if I want to create a policy gradient, first I have to create a parameterized policy, and then I have to test the policy, and then I have to see if I can generate samples from it, and so on. And this is being done on Data Cabinet, which is sort of a cloud-based system which will feature, I guess, area specific. How would you call them? So I'd like to call them environments, but it's more like they're sort of neatly pre-installed or pre-installed environments where you won't have to do any sort of installation. It's sort of a plug and play model for being able to get up and running on uh, data science or other programming or educational needs. Um, and uh, we will be adding more features as time goes on, and from our perspective or from my perspective, what's very helpful about it is that you can, for example, I was eating breakfast earlier this morning at Panera Bread, and I wanted to test out some models, but of course I wasn't lugging around my computer, but I could easily just sort of start it up on my phone and just sort of start running the cells and try to start doing some debugging and trying to at least run some simulations. And if something wasn't working, I could change it in real time. So there's a lot of applications, and in general, it's about having access to very easy, direct access to um, to, I guess, more heavy-duty computing resources. And without further ado, I will get started here. And as I mentioned, we'll be covering actor-critic algorithms. It it would be helpful if you were if you have some knowledge of well, if you were somewhat familiar with what we covered the last 2 weeks, I will sort of more briefly go over some of the concepts. Um, but the actor-critic model is very heavily based on policy gradients with an adaptation of value functions. Um, so I think I'll bring up some of the earlier notebooks as well, which might give some clarification. And also I can bring up some of my earlier slides as well. But let me get started. And for those of you who haven't haven't attempted to run one of these notebooks, we should have shared an import link in in an email from Data Cabinet earlier, I guess yesterday or earlier this week, and it gives instructions on how to import projects. And there is a special code that So once you log on and create your account, then you can create you can import a project and enter the code, and it will sort of create the environment for you. You don't have to do any sort of conda installs or or pips or anything like that. The one thing that we have to do at the beginning, and I have already done it in this case, is that um, we have to install the OpenAI directory. And so in the case of so if you haven't done it before, what you would do is that you would change this to, I mean, right now we change this to Markdown because we don't want it to actually run. But but if you haven't done it before, then you would change it to um, an actual executable cell, the code type, and then you would just execute it, shift enter, um, and it would and you'd see a lot of messages about installing the different OpenAI environments, like the Joko environments, Atari games, and so on. So, and these are just the normal dependencies. But let me start with just sort of um, with, like last time, a bit of a higher level overview of what we're trying to do here. And I also wanted to bring up, um, for a quick review, what we did for policy gradients last week. So last week, what we did was policy gradients, um, and there was a so there are a few reinforcement learning terms which hopefully you should be a bit more familiar with by this point, and that is there is the agent, which is making the decisions, the environment, which is controlling everything, which is basically everything else that just makes up the agent, the state, which is sort of which is a what's happening in the environment, the actions, which is uh, what the agent decides to do in terms of behaviors, and the policy is how they is some sort of strategy or some sort of methodology for how the agent is going to make decisions given the state. And the reward is passed on to the agent, and the agent uses it to shape behavior. So if you get a positive reward, if you take some action, you get a positive reward. The agent will think, oh, that was a good idea, so I will try to do that more in the future. And if you take an action and get a negative reward or a worse reward, then you'll be less inclined to do that. So that's basic um, reinforcement learning. It, it's the same as in biology as in just data science. And um, the the general idea, of course, of reinforcement learning algorithms is this concept of policy iteration. You can sort of summarize most reinforcement learning as policy iteration, where you have some amount of sampling, where you have given your policy, then you will start sampling simulations, or you'll do some sort of real world testing. Like maybe you're playing a game of chess and you're sort of building your idea of what you should do in certain board states. So that would be your sampling, and then there is policy evaluation, um, which is given a policy, you're trying to evaluate if you're in a certain state, then how good is that state? And you can also do that for state action pairs as well. Um, and there are a few examples of that, like value function learning, Monte Carlo evaluation, and temporal difference learning, which we'll sort of talk about after the initial Actor-Critic example. And finally, there's policy improvement, which is uh, if you have once you've evaluated your policy, you can now try to get a better policy, and more in generally speaking. And for example, for Q learning, then we tend to do something called epsilon greedy learning, where we literally figured out what the best possible action is with each state, and then we use that to define a new policy. And policy gradients, which is we're actually going to take the gradient of some sort of objective and use that to calculate um, and we're going to take the gradient of the policy parameters with respect to a certain objective. And and I just wanted to go through this quickly because it's some amount of background, and please oblige me on this. And for policy gradients, the general outline of work, of course, if you want to create one, is that first you want to do a policy gradient, so you need to create the policy. To do that, you need to create a parameterized you need to sample from the policy because a policy determines action probabilities for each possible action, and but that's a distribution, so you actually have to sample from that in order. You have to figure out a way to sample from that. You need to roll out. You need to actually run some sort of simulation using the new policy, which is roll out and record the trajectory, and then using that information, you can calculate a policy gradient with what we call with the score function with um, the log policy probabilities times some feature rewards. And finally, that you can use a policy gradient to update the policy, and then you can start sampling all over again. So let's go back to the Actor-Critic algorithm, though. So this is very similar to the policy gradient. So the question is, well, and if you'll notice that we've actually taken many pieces which are from the policy gradient algorithm, and one question is, well, how is it different? And the big key is that, so let me see if I can open the policy gradient. The big key is that for policy gradients, what we did was we relied on feature returns, and there is a certain equation which we use to define the for our objective. Let me have a well-formatted example of it. Here it is. So our objective was that what you're trying to do in a reinforcement learning is you're trying to maximize future returns. And given a certain, well, if you run the simulation with a policy, like pi theta, then you're trying to maximize your expected future returns. And the way we can calculate this objective function is by calculating the, well, what we do is we take we sample from the grad log probability of the policy, and we multiply that by feature. This is slightly off. This should be expected future returns. And this is the most basic example, and it's what's known as a reinforced algorithm. So the big difference is that, so the issues which we brought up at the end of last week was that expected future returns are very noisy because it's for each case you're going to plug in the rewards from a single sample, and that will highly depend on. Remember, there is some stochasticity from, even if you choose the same state and same action, then there could be some stochasticity of the system where you might end up in slightly different states. You might end up in different states even given the same states and actions. And also the rewards could be stochastic as well. For example, if you're playing baseball or something, or you could try to hit a pitch. You could be a batter trying to hit the baseball, and sometimes you're going to hit it, and sometimes you don't. You might swing the exact same way, but sometimes you're going to miss. So, and the reward might be negative or zero if you strike out, and it will be some positive value if you got a hit. So even if you make the same action, you can end up with in a different state, and also there could be a different reward for each. And that's sort of an example off the top of my head. There's probably better ones. But anyway, so the issue is that, so these rewards are single sample rewards, and each of them is going to have, each of the feature rewards are going to depend on, they're going to change based off of the stochasticity of the reward function itself, and also what sort of future states you end up in. And so that's an issue. What we really want to know is we would want to know the expected value of we would want to know the expected feature rewards instead. And this actually brings us back to the first lecture, or the first week, where we briefly talked about value functions. Scroll down here. So what we're trying to do is we're trying to, so here we go. So this is, well, this is this is sort of a mathematical representation of future rewards. So future, given a time step t, then you want to calculate the sum of all future rewards after t. And you can consider, well, there's some theoretical point about how you can also consider the rewards prior to that point, but then they don't actually matter due to causality. But I think I had some short discussion on that, but I think it's a little bit tangential and unnecessary. But from this, if you think about it, the definition of a Q function is that given a certain state and taking a certain action, what is your expected future rewards? Well, that's actually the exact same. That's the same. Um, that's the same value, or it's exact same things what we're talking about before. So what we're actually trying to do in terms of determining future rewards, if we're not thinking about empirical sampling, if we want to know like the true future expected future rewards, what we want is a Q function. So if we can approximate the Q function, then and the Q function will probably, it's going to be, if we know the true Q function, it's not a stochastic value, it's an expectation. So it's going to be a lot less, there's going to be a lot less variance involved, because we don't have to consider, it's sort of adding together all the future possible states and all the possible um, um, variances in the rewards. So it does that all for us. So what we could just calculate the Q function, but then that's not always that easy, because for a Q function, then, well, especially in the non-discrete case, and there are a lot of states and actions, and so we probably want to do some sort of parameterization of it. And the other thing is that there is still some variance involved, and so one thing that we can do in order to so a lot of this is basically dealing with the issues that policy gradients have like high variance, and if you have high variance, then you're trying to perform stochastic gradient descent, it's not going to converge very quickly. So what they've tried to do, or there's a paper, they tried to subtract some sort of baseline function. And this is sort of talking about the stochasticity, the time dependence. This is where I'm not going to talk about that much. So what you can do in order to remove some of the, so it turns out if you subtract a fixed value, or I'll generalize a bit more later, but if you subtract a fixed value from the policy gradient, it doesn't actually change the policy gradient, but it will reduce the variance of the policy gradient. So what they try to do, so the idea is that you want to find some sort of baseline measure that you can subtract from this Q function, and that will help minimize the variance. And so the question is, well, how do you find that baseline? Well, you could calculate it very literally by taking the average. You could take all your samples and just take the average expected future values of the Q function. Or what you can do instead is there's this, well, what I'm trying to get to, there's this result by Andrew Ng, who did the I think he did the Coursera course on machine learning, and he's pretty well known in the deep learning community. But he wrote this paper called Policy Invariance Under Reward Transformations: Theory and Application to Reward Shaping. And basically, he proved that if you have a certain type of function which is state dependent, if you have something which he called a potential function, then it will not change. You can reshape the rewards without changing the MDP. What that means in practice is that you can subtract a potential function, which, and in our case, it's going to be the value function from the Q function, and that will that will help us, that will give us close to the best possible um, minimization, that will help minimize the variance of our policy gradient estimate the most. So I realize that I've been talking a lot about this, and maybe I should switch directions to showing what we're doing here. So there's a few lines earlier on in the code where, if you might have noticed, so if you start working with trying to code some of these things, especially this carpool, this carpool environment, it turns out that there are some issues involved, and just early on, I finally figured out some workarounds for it. TensorFlow uses, this is an aside, so, but TensorFlow uses float 32, but carpool uses float 64, and deep learning doesn't actually require that much precision. So one of the tricks that they do is they tend to lower the precision in order to speed up the process. So what I basically define the function to change it to float 32, and also TensorFlow wants to create the tensor. It doesn't accept just a normal n-dimensional array. It wants a 1x4 tensor. It just creates the function to handle that for us. Okay, so anyway, I'm going to parse through this here. So we've replaced our we've been trying to replace our feature awards uh, with this thing which we call the advantage function, which is the Q function minus the value function. And if you think about what that is conceptually, it's sort of it's the advantage function, which is uh, Q of SA minus B, is how much better a certain action is compared to the average compared to just the average outcome for if you just follow that policy. And what that means from a policy gradient point of view, I can go back to this formula here. It's that when you do a policy gradient, you have this log probability and you're multiplying it by this sort of advantage function or feature reward function. And it means it's the greater the advantage, so the better a certain action is compared to just the average action or compared to average, then the more you want to increase the probabilities in that direction. And if the advantage function is worse than average, you want to push down, you want to lower the probabilities of choosing that particular action. So that's sort of the conceptual understanding of what the policy gradient is in terms of advantage functions. And um, and all this is a lot of talking about, but basically what we're getting to is that this main difference between policy gradients and actor-critic algorithms is that we need this value function. We need a parameterized value function. For the Q function, there are different ways of dealing with that. One is to just use feature awards like before. But let's focus on now creating this parameterized value function given a certain policy pi. And we're going to create this in TensorFlow. And then the idea is that there is this true value function with respect to a policy, but we're going to try to approximate it with a parameterized value function using a deep learning model. And so it's actually similar to it's fairly similar to the policy function in the policy gradient slide. But we're defining this initial value function using TensorFlow. This is just the typical scoping. And so we're feeding in a state vector, and then this is just we're just doing matrix multiplication off of the state with a weights and adding a bias, and then we're adding this nonlinearity, and then we're doing a second layer where we're also doing matrix multiplication and we're adding in a bias, and then we're using that to return a value. So it's pretty straightforward, I think, sort of a two-layer deep learning model. And we can test, so we can test it out. Earlier on, we just did a quick little simulation for Cartful, and we returned an observation, so we have an observation ready for us. And we have a randomly initialized value function, and we tested it out, and it gave us this value for this particular observation. It outputted this value, so we know it's working. So our goal, remember, is that we want to. So technically, we need our value function to be close to the true value function b pi. And well, the question is, how do you do that? So what we're going to do is we're going to try to minimize. We're going to find the theta such that b theta is close to b pi. So that means we're going to try to minimize the distance, some idea of distance between b theta and b pi according to some sort of distance function. And this brings up two questions. Well, what is the true value function? And the answer to that is that we can do what we did before. We can use empirical rollouts to estimate the true value function. And if we're going to do that, remember this is a value function with respect to a policy, so we're going to have to make sure that we've defined a policy function and then a policy sampler, and then and have our rollouts like before. And so that's these slides below, or these cells below. We define the policy act, and then we defined a rollout to do some sort of simulation based off of that, and we can use it to calculate the true value function. And this is a test put to make sure that it's working. We can generate a rollout just like before, just like in the policy gradient. And at the very end, it returns the future awards for different iterations for different episodes. No, actually, I think this is a future awards for one episode, and it's doing it for each time step. So you can see that the future awards are because they're adding on to each other. Then it's like the further you go on, you don't count the earlier reward, so it's slowly decreasing. So we've created a value. Well, so now we have our empirical estimate of our value function, and now the question is, we have a parameterized value function, we have our empirical estimate. So the question is, so how do we determine what the distances between these two value functions? And so let's think about this a little bit. For the discrete case, this isn't an issue. It's like for the Q-learning case, we have these discrete example. We have this. We have these cases we had where we had discrete sets, a discrete number of states and its discrete numbers of actions, and we could just create a table for each state and each action, for each state action combination, and so that wasn't an issue. But remember, this is parametrized, so we can't do that because there are infinitely many states. So we have to optimize a separate theta for each state. And so what we can do is we can integrate over, since we have this sort of continuous state space, we can integrate over the state space. We can have some comparison between the value v theta of a given state and our empirical estimate of v pi at that state, and we can sort of integrate over that. And the only issue is that, well, what if we just did some sort of uniform integration? But when we think about it, we probably want our policy to weight the states that we visit more than the less visited states. So
so maybe our policy will, there's some case where there's some far off example, like it could be for some chess game where there's some board state where which you will almost never see in real life, or against any opponent. And maybe the policy is very different than, maybe the policy is very different than our empirical policy is different than our parameterized policy function, um, in those sort of edge cases. But since they're so rare, we don't want to weight them as highly as much more common cases. So the more the more often you'll see a given state, the more we want to weight that. And this sort of makes sense. For example, if you think about, well, it could be good or bad, but if you think about, like, let's say if you're trying to build a self-driving car, then or if you think about a human who's learning how to drive, which is, I guess, a similar issue, then you want them, in order to maximize their policy, you want them to be able to deal well with most reasonably common situations. And if there's much stranger situations, like the car is like falling off a cliff or something like that, and it's you don't necessarily have to optimize for that because, well, it's not going to happen that much. So, I mean, um, for in more reasonable circumstances than in less reasonable ones. Um, so so anyway, so what we want to do this sort of integration in the natural weighting for this is going to be this. We can sample from the states, and based off of our sampling, that'll sort of give us a distribution of of which states are more popular, or technically which trajectories are more popular. And so we don't even have to know the probability distribution. Our sampling will tell us the distribution for us, and we just have to figure out. We just have to integrate. We just have to take this empirical sampling of trajectories, and then um, and consider the difference between the parameterized value function and v theta. Um, and there are different ways. There are different. Well, one small question is, well, you could there is you can consider there are different ways of measuring distance, or you could take an absolute value, but we're going to take a mean squared loss. Um, there's I think a Huber loss is also used sometimes, but in most cases, a mean squared loss is more popular, and it has some more meaningful probabilistic properties as well. Um, so in terms of what we're doing, it's actually, we don't really have to do that much. Uh, all we're going to do is we're going to run what's the TensorFlow function, the L2 loss function for the difference between V calculated and V predicted. And so we can expand our value function. Oh, we can expand our value function to a um, more of a general method. And you'll see that this is almost exactly the same value function as before, but we're defining we've calculated our difference here, and we've defined our we've defined our loss function, and then all we need to do is we just have to run some sort of optimizer, in this case TF train, the atom optimizer, with some sort of learning rate to minimize the loss, and that will handle training the value function, fitting our parameterized value function to be as close as possible to our to the true value function given a certain policy. Let me just. So I think I was idle a bit too long, so I need to wait a little, and I can log back in. So I won't be able to execute the code in the meantime, but I've already run it before. So let me ask to see if there are any questions for now, or if there are any technical issues. So people should have access to this notebook so they can sort of play around with it. you could try things like you could try a different loss function if you want. You could try a different uh, value function architecture, um, and uh, later on we're going to consider different. Um, well, I guess those are most of the options that we're considering for value gradients for now. But like for example, you could instead of a 2-layer neural net, you could do a 1-layer neural net. You could increase the number of hidden layers. You could do other things. Anyway, it seems we're fine for now. So now, we can actually, so now that we've defined our value function, we can replace that in, we can replace our future, we can use that to calculate the advantage instead of future returns in our policy gradient. So now we're going to create we're going to expand the just like in the policy gradient notebook, we're going to define a policy gradient function. And if that helps. Okay, so we have a policy gradient, and so it's very similar to, so everything is exactly the same as before. Up to this point, we have our policy model, we calculate the probabilities, we calculate the score function, um, and finally, the difference here is that before we use future returns instead of advantages, and now we're going to replace that with our advantage vector, and later later on in the code we're going to define the advantage vector. But for now, what we've done is we create a placeholder which will accept a tensor for the advantage vector. So it'll be episodes by, it'll be the dimensions are a number of episodes by 1, and so it's just this one change within the policy gradient code, and you can just consider it like you're just renaming it. Otherwise, it's exactly the same. And then we can roll it out like before. And I just want to point out the change where we calculate so basically the policy gradient function, policy gradient code like before, but we're going to, at some point, we're going to calculate the advantage function. Okay. Well, whatever. So remember that to calculate our advantages, we need to subtract our Q function from our value function. So our Q function is basically going to be the future rewards that what we can use is the future rewards which we calculated before. And our value function, we're going to use, so we created this model which will, we created this model, this policy gradient method, which one of the things that will return is a TensorFlow operation for generating the value of this given a vector of states. So which here is V calculated, and at the very top, let me show it here. So I called value grad, and then it returned the calculated VL state, the new values, optimizer, and the value loss function. And if you look at the value gradient, I'm returning here H2, which is the calculated value function, and then it's returning the state which it was fed in as a placeholder. It's getting the new values, which is the returns, and the optimizer, and the loss function here, and the optimizer here. So with TensorFlow, you can call the optimizer. Once you return the optimizer, you can call it and run it when you train models. We've added this line so we can have be calculated and be optimized, VL optimizer here. Scroll back down to where I was before. So here it is. Okay, so here we have VL calculated. We're running the session, the TensorFlow session. So remember, for TensorFlow, you actually have to it creates a computational graph for you, but you actually need to run the session on the tensor in order to calculate the values for it. And remember, to calculate the values, we need to feed in the states. So we have to use the speed dictionary command for the observation vector. So we're using that to calculate the current value. And we have 0, 0 for the indices. So we've calculated our value functions for each state, that's current val, and we're subtracting that from future reward, which we calculated like before in policy gradients, and that's our advantage vector. So now that we have that, well, one thing that we want to do, two things. First of all, we want to optimize our value function, and we're going to run our value function optimizer, which our value gradient function returned before. And to do that, we have to feed in all the placeholder functions. So the speed dictionary in TensorFlow, it defines all the tensors the placeholder tensors that you're feeding in. So we have states, future returns. We need states, future returns vector, and then this line is going to train the value function for us. And remember, for the policy gradient, we need the advantages vector. We're replacing future returns with the advantages vector. So now we're just going to run PL optimizer, which is our policy optimizer, and we're going to feed it the states and advantages. And states, advantages, and actions. And once you do that, it's going to optimize the policy for us. And at the very end, we can return the total reward for this episode. So actually, as a summary, what we did was we created a value function, and we defined this sort of L2 loss for it, and we have an optimizer for it. And we calculated the values, a vector of values using TensorFlow for each state, and then we calculated the advantages, and we trained the value function, our parametrized value function, and then we used our advantage vector, and we replaced that with our future returns, and we use that to train our policy. And that's one example of the Actor-Critic model, and I'm hoping I can log in so I can just show this a bit. That is interesting. Okay. So I'll continue for now. And so you could just run all, and it will work from beginning to end. And so we've altered our policy gradient code to incorporate value functions. and to use advantages instead. And we're going to now execute it like before. And it would look a lot nicer if it happened this time. But, out of there. And if you get lucky, you can run it and it's actually going to it will completely train the model itself. And you'll find that it gets much better results from before. So I've updated the policy gradient code so it actually completes in a reasonable amount of time. Part of it was Actor-Critic. But usually I'm seeing on average it gets expected returns of around 25 or around 25, but you can see that this Actor-Critic model it does a lot better. It's doing in this example here it got 110, and there was one case where I guess it had very good initializations and it actually had it was able to reach like the ideal rewards of 200, and then when I ran rollouts it got about 195, so it was close to optimal. Okay. So let me get this loads. I'll try to run it for you guys. So you can see here, well, if we pretend that I was running it, it takes about around a minute to run, I think. And well, let me stop for a second and see if we have any questions. Hopefully it'll load in time that I can run some wonderful simulations for us. So now it should be running for us. It is now, in the policy gradient example, it ran a little bit slower, so I changed the code so it told you when it ran 100 iterations. This one's reasonably faster. And after that, I'm going to run a rollout for it for one episode, and I gave it a render option, so it'll actually show us. For training, you don't want rendering on because it slows it down. But of course, if you want to see what's going on, you can see how well it's doing. So yeah, so great. So this one was actually had well, you call it somewhat lucky. It had some good initializations that at some point it was able to reach near perfect performance, and on average the reward was 1,479. No, that's not good. Well, we'll see. So we'll run a rollout, and it's going to run a simulation for us. And remember, this is completely random initializations, and it's learned to sort of balance this part to like balance a stick on top of the cart as long as possible. This is a little slow. It's running fast on my computer. Oh, sorry. It's still, I think it's still training here. Okay, well, we will continue. Well, if I can, I'll get back to this a little bit later. Oh, here we go. Oh, yeah, so now it's, you can see that, so there should only be one here if there's some sort of clipping problem or wrapping problem. But you can see that it's moving it back and forth and it's balancing almost perfectly straight up. So it is learned to perform this task. I believe they mentioned that like there's an OpenAI environment which uses policy gradients for humanoid walking. So you can probably do that as well, although the problem is a little bit more complicated. This is only 4 dimensions of observation, possible actions, but it is learned to. So it got a reward of 187 out of 200, so it's a very ideal performance. Better than what I could do. If somebody randomly gives me a cart in the phone, I don't think I can do it as well. So that's a great example of actor-critic models. Well, before, I mean, we had an example of policy gradients. This is an example of actor-critic methods, and it's working very well. So now I wanted to. So this part I've been trying to get to work, but it's now. But it's so I want to talk about a few more sophisticated variances or variations of actor-critic models, and so the key is that before. Let me go to this slide. So the key is before we were using Q minus feed, so future rewards minus our calculated value function. And remember, future rewards is still a fairly, it's not ideal if you will have to calculate a full Monte Carlo rollout. What would actually be better is if you could have some faster, simpler way, although it will be more biased, but of calculating the Q function. And this brings us to a very important, it's a very important equation in, I can zoom this in. Okay, yeah, this Bellman equation. The Bellman equation is for both value functions or state value functions and state action value functions. So the V function and the Q function. And they have, they're slightly different, but in both cases you have a very similar format. And it's that when you have the correct value function, then this equation is true, that the Q value is going to be equal to sort of an expectation of the reward plus some sort of discount factor times the expectation of the Q value of the next state in action. And this is over a distribution of next states in action. So you take state, you start in state S, and then you take action A. And then you end up in a new state S prime. It might be deterministic, it might not be the case, but it doesn't matter because we're taking a distribution over it. And then you're going to choose a new action. You'll choose a new action based off of your policy, off your policy function. So you're going to select, given S prime, you're going to select an action A prime. And of course, that's stochastic. The policy might select different actions but there are different possibilities for the actions given the state. But if we take the expectation over all of this, we're going to get this Q function. And this relationship is true. And if you think about it, what this means is that if you want to calculate your expected future rewards, well, you're going to, from a given state and action, you're going to calculate your reward for the next time step. And then if you have a good estimate, and then if you know exactly what what the Q value is for the next state, or for each possible next state, and then you know how to run the expectation over that, then it's going to give, this is exactly the same as the future returns, because this Q value is the future returns from state S prime given action A prime. So so
it's a very important equation. It occurs a lot, and there's a lot that you can say about this. Um, and in our case, well, um, there's a lot of mathematical properties about it too. But the most important one is, well, they call it a they call it you can define it as an operator and you can call it a contraction. But basically, the most important thing is that if you even if you're not at the optimal, if you don't have the correct Q function, if you run this, if you think about this as sort of an operator to update Q instead of a quality, if you think of this as an update, a better estimate of a better update or better estimate of the Q value, then it's going to get closer and closer to the true Q value function, closer to the true Q function. So if you run this enough, it will converge under certain circumstances. Most in most practical cases, it will converge, or at least enough for our needs, to the true Q value function. So this means that we can estimate, if we can just estimate a Q function, then we don't actually have to do all the work of calculating future returns. We can just look at the returns for one step, and then just sort of update our Q function. So that's one concept of it. And so remember our advantage function was just the Q function minus the value function. So what we can do is, so this is an expectation, but we can approximate this expectation by using a single sample estimate. It's not going to be exact, but if you do it enough times, then it's going to be accurate enough. So we're going to use a single sample as estimate as a sort of update to our Q function, and so our advantage function becomes R plus discount times the value function at the next state. So that's our sample. Instead of considering all possible next states st plus 1, we're just going to sample and take st plus 1, and we're going to subtract the value function. And there are a lot of interesting things I can say about this. One is that if you go back to Andrew Ng's paper on baselines, this is actually the definition. It's a necessary and sufficient condition for being a baseline function, which will not change the MMP. So it will be this is basically the sort of the ideal form of a baseline. So this means another way we can think about this is that this is sort of the difference between our Q function and so this difference between it's sort of, well, let me move on past that, but it's I guess what I want to talk about next, it's based off this. This is going to give us the idea of temporal difference learning, because this is sort of you could consider this as a one-step look ahead, where so instead of calculating all future returns, so RT plus 1, RT plus 2, and so on and so on, we're going to replace RT plus 1 all the way up to R infinity with just this value function instead. And what we can do on top of that is, so you can consider this to be a one-step look ahead, but we can chain this together. We can recursively chain this together and then unpack this even more. So the RT plus 1 plus gamma times expectation of QS prime prime and A prime prime. And you can do this for n steps. So let me see if I can scroll. Yes, I can scroll here. So what we can do is if we do an n-step look ahead, actually these
these gamma v terms and minus v terms, they'll cancel out for all intermediate terms. And what we'll get is RT plus gamma times RT plus 1 plus gamma 2 gamma squared times RT plus 2 all the way to gamma to the n minus 1 to the r to the t plus n minus 1. And finally, we'll have, might be minus v. And at the very end, we'll have our, yeah, I think there should be a minus v. But basically, we're going to add up all the returns from, like, for n steps and then subtract the value function. And this is, you can consider this to be an n-step look ahead instead of a one-step look ahead. And you can also consider the Monte Carlo function to be an infinite step look ahead. So they call that TD0 because for a reason that I'll get to. Or no, I think TD1 for a reason that I'll get to. So, and this goes back to the concept of a bias-variance trade-off. So the Monte Carlo functions have Monte Carlo rollouts have very high variance, but they're not biased because you're doing empirical sampling. Whereas if you don't actually know the true value function, then the one-step look ahead has a huge amount of bias because it's dependent upon how correct your value function is. But then the more steps you take, then I mean the less bias there is because you're using more empirical rewards, but then you're increasing the variance in compensation for that. So what they do. So one idea is that one thing that they do is that they can they can add all the, so these are the n-step returns, but there's a way that you can, if you do an exponential sum of the n-step returns, so exponential over n. So here we have gt of n, and then we multiply it by an exponential factor of lambda to the n minus 1. Then what we're doing is we can combine all these different terms which have different ratios of bias and variance together, and we can form at the very end sort of a alternative estimate to a one-step look ahead, which is over here, or an infinite step look ahead, which is Monte Carlo sampling. And they call this, so if you create the sum, then it's called a TD, so one step look ahead is called TD0, and it's infinite, this sort of sum of n-step look aheads with a discount factor of lambda is called TD lambda. And then we can use, and instead of, in order to update our Q function, we can use this GT lambda minus V. Although it's pretty interesting, but actually we don't need all of this. The most important thing is to introduce this concept of temporal differences of R plus gamma V of minus V. So we're going to use that. What we can do is that we can use that instead of calculating our full Q function. But when calculating our advantage function, we're going to replace the full returns minus our value function approximation. So, so this is actually fairly reasonable to calculate because when we do our rollouts, we have all our rewards, and we have our we have our states, actions, rewards, and the next state. So we have records of that, and we have our value function. So our value function approximation. So all we have to do is to just record each separate reward, and then calculate the value function for the next state, and then the value function for the given state, and then we can use that to calculate the advantage function. Okay. So I modified the Actor-Critic algorithm, and this is it's similar, but then I changed it to a class because, well, the issue was that um, in order to calculate the advantage function this way, I need to calculate the policy for the next state and the policy for the existing state. And the previous version of the value function, I inputted the state value function, but I didn't want it to. Well, I wanted to. It should flexibly accept both, I guess. If that makes sense. And I created a separate MVP model, which is actually giving me trouble right now. But here is, so pretty much the same code as before. The difference is just return target. It's just the predicted values minus the return target. So the fitting for the value function is the exact same as before. We're just using this L2 loss, and we're training it a similar way. And sort of a batch version of the value function. Here, so here we are is we have the separate function for calculating the advantage function. And what we did is that we took in the rewards, and then we calculated state value for, for time step I we took the reward, and then for time step I we took the state and we calculated the value function for state I, and then we calculated the value function for the state I plus 1, and then all we did was take reward plus the discount factor times the next state value, and then subtracted the existing state value. And we can use this to replace the advantage function in R. So this gives us an advantage vector. And so this isn't in the existing notebook, but I was just trying to make it work. But let me show you where we changed it. So I call that function the advantage vector TD0, and actually the code itself doesn't change because for our TensorFlow version of the policy function and policy update, it doesn't ask how we got our advantage vector. So we actually calculate it separately, and we calculate it outside of our policy function loop. And so we just calculate a different way, but we fed in just the advantage vector as before, and it's going to update the policy the exact same way. And this is sort of a TD0 version of actor-critic algorithms, and it's actually much more popular than the one where we calculate the full future awards and use that for the Q function instead. So I have to fix a few bugs in it. For example, if there's some sort of initializations problems with it's a very common thing in TensorFlow. Make it work, but that is so. We have a full example of I guess the simpler version of the actor-critic algorithm, and then over here we have a work in progress for a more common example for the actor-critic algorithms. And finally, there's a more advanced version. I think A3C uses it as well, and it's called. It uses a different type of advantage function estimator than this, but it's based off of a very similar idea. And they call it a generalized advantage estimator. So this is more for curiosity/research, for your own research purposes, or for your own intellectual research purposes. But for generalized advantage estimators, we're going to do a but anyway, so we have this term R plus gamma to the nth power times v to the. So we can do this sort of telescoping sum of these terms. This is right. My figures.
but basically, we're going to do the same principle as in 3D learning, where we have a telescoping sum of the value functions. There's some sort of cancellation, um, and so we're going to create these sort of like n step approximations to the advantage function. Well, anyway, um, and then we're going to and each of them is going to be have and each of these ANs is going to have this different balance um, of variance versus bias, and we're going what we're going to do is we're going to sort of add them all together with as an exponential sum using uh, using lambda, and we're going to create something called um, we're going to create an A lambda version of the advantage function estimate. And I don't have an example of that, but I might have maybe a slide which has that. Let me look at this. That's in there. So here is something from the Berkeley RL course, and um, so we're talking about general advantage function estimators, and yeah, we have gamma n to the v s t plus n and minus v of s plus I guess the discounted reward at that point, and um, so yeah, they define each of these as I think they each of these expressions they call delta, and then they add them all up into some sort of exponential sum of all these terms together. So then it becomes here gamma lambda to the sum power times um, times this sort of well, they call it an eligibility trace, um, and they use this as and so for both TD lambda and this general advantage estimator, I mean, it sounds interesting theoretically, but impossible to calculate because you have to calculate infinitely many terms. But there's a trick behind it in that you can express it, you can sort of calculate it recursively as you go through the trajectories. I wonder if they show that here. Using something called an eligibility trace. Um, anyway, you can look that up, and it gives, and it's sort of a more advanced method of calculating an advantage function, which is very similar to, it's sort of a combination of TD, um, of the TD method of advantage functions and the Monte Carlo method, which we did before in the first example. And I guess that's most of, I mean, I wish I could have, I had a bit more, uh, I could cover eligibility traces, like I had more material to cover more thoroughly, um, but I don't have that prepared right now. But for now, you can play around with the actor-critic algorithm, and hopefully everyone understands the basic concept behind that. And also, um, I getting used to this concept of temporal differences instead of Monte Carlo. It's actually something which is part of just normal value function approximation and Q-learning, but I sort of separated it for now because it's sort of there's a lot of concepts thrown at people in the first um, class or in the first week, so I thought it was a bit too overwhelming. Um, but I wanted to introduce it here because it had a very important purpose for this actor-critic um, value function estimation and advantage function estimation. So if there are any questions or technical difficulties, then we can help with that. In the meantime, actually, what I want to do, I think I timed out again. So
while we're waiting to see if there's any questions, I just wanted to um, show the policy gradients algorithm. So remember, for our actor-critic algorithm, we actually got pretty lucky and that had a performance of 195 for the rewards for our single test. It was really good. And but now the policy gradients, I sped it up a lot, so it can. And before it trained, it was fully operational and it trained, but it trained fairly slowly. But I made it a lot faster. Yeah. I'm going to just run this all, and then we can see the relative performance. Simulation. I also had a small update to do this, to change everything to float 32, which was one of the speed ups. So I put that in the policy gradient code. And the other thing was, I think I changed the action probabilities. For more efficient sampling. Samples. Okay, yeah, so it's training right now, and so it completed while I was watching it fairly quickly, and it had a performance of, so before it had a performance of 195, and I think the Actor-Critic got like some earlier examples, it got like 100 or something. So not perfect, but like not bad. But this one got 10, so or much worse. And we're gonna test it again. Um, and you can see that it was sort of it's you can notice that it's like falling down a little bit more. It's not as in control, so the policy isn't nearly as good. And that's probably technically, if you trained it long enough, then it would read similar performances. It could read similar performances, but the variance is just too high with just the standard um, full empirical returns um, version of instead of our advantage function. So I guess so. Yeah, so you can test out both of these. You can, of course, you can play around with. You can choose different policies. Um, you can, I think, for the Actor-Critic, you can try different loss. I think there are a few things that something you can try. You can try different loss functions. You can try different networks. You can try the TD0 version, which I'll try to get that up and running earlier this week, upcoming week. And you can even try to get the general advantage estimator version working as well. I think there was something else. Well, I guess I'll mention it later in the email. But anyway, thanks everyone for watching, and I hope this was pretty interesting. In the following, we're going to update the note. I've been continually updating notebooks. But I guess what I'm going to try to do in the future is I'll probably, I don't know if it will be in a sort of an online workshop or not, but what I'll try to do is I'm going to try to put together a lot of this very interesting deep learning or gather a lot of interesting existing deep learning notebooks that you can just run and have all the dependencies installed for you on Data Cabinet. So we'll have this folder directory of that, and then like you can run Heatstream or whatever without any sort of setup, or and maybe GANs and just some sort of GANs or adversarial image generation. So we'll have a lot of interesting projects that you can sort of plug and play and test on your own and see how they work and mess around with them. But thanks everyone for joining, and I guess have a great rest of the day. Thank you.